Hi, let's discuss an important topic. Why votes should follow Benford's law, or why anything follows Benford's law. Why any real world data, subject to certain restrictions, follow Benford's distribution. I have already covered Benford's distribution in another video, especially in regards to 2020 US presidential election. This is a follow-up video on that. So before understanding that, we should look at two things that characterize a population or numerical data: mean and standard deviation. Mean is pretty self-explanatory. It is just the average of all observed values. Standard deviation is a measure of dispersion. That is, how far is a value in a data relative to its mean. Standard deviation has a simple formula. It is the square root of summation of squares of all deviations from mean divided by the total size of the sample. Let's look at a real-world example of how mean characterizes a population. If we look at length of animals, blue whales are generally around 25 meters in length, that is 2500 centimeters. Mice, on the other hand, are around 7 centimeters in length. It is worth asking whether it is more likely that you will see a blue whale with a size of around 5 centimeters more than its average, or a mouse with a size of around 5 centimeters more than its average. Because blue whales already range from around 2300 centimeters to 2700 centimeters, a 5 centimeter increased length can still happen. But for a mouse, a 5 centimeter length increase would nearly double its size. Only those mice are likely to be around sizes of 12 centimeters, whose average is also around that. Similarly, applying it to voter turnouts. Imagine a city with an average turnout of 100,000 people because of large population as compared to a rural village with an average turnout of 10,000 people. Is it more likely that you will see a voting turnout in the city that is around 500 more voters than its average, or a village that is around 500 more votes than its average? Of course, 500 extra voters above mean in a population of 100,000. Of course, 500 extra voters above mean in a population of 100,000 is a lot less surprising because it is only a change of 0.5%. But for the rural area, a 500 increase would increase the total number of voters by 5% above mean, which surely is something to notice. This is because generally, when the mean is higher, we would expect standard deviation to be higher too. A dollar increase in price of a pouch of ketchup is huge, but not on the price of a car. This is why to estimate dispersion in a more comparable manner across populations or samples, we use what is called coefficient of variation, or CV. It is the ratio of standard deviation and mean of a data. Distribution with CV less than 1 are considered low variance, while those with CV greater than 1 are considered high variance. Let us assume that coefficient of variation is 1. According to central limit theorem, a sufficiently large sample of population with a defined mean and standard deviation must evidently close on to a normal distribution. This means that if random and independent values are taken from population, as the sample becomes larger, the distribution of such values would approach a normal distribution. Let us now look at how the distribution of such sample data would look like, taking mean as 1 and same for the standard deviation. If we have such a distribution, to find probability of occurrence of a value that changes the leading digit to 2, we just enter that the x should be greater than 1.99. There is around 16% of chance of finding an instance where the value observed would change the leading digit from 1 to 2. Now let us test the value for a mean of 9. We also take standard deviation of 9 because the coefficient of variation is to be kept 1 to ensure comparability. Now what is the probability that the leading digit would change from 9 to 1, which would of course come with a value of 10? It is around 45%, which is more than twice as what has been calculated before. Now what if the leading digit again becomes 1, when the mean is, let's say, 11? Then for the first digit to change to 2, we need to look at values greater than or equal to 20, which only occurs with around 20% of probability. This is what will give us the Benford's distribution. When we have voter tallies for a candidate, they would vary across a finite range, As seen above, it's far more likely that in many such observations, the voter tallies with the averages that start with 7 or 8 or 9 have shifted to other digits than to expect that the voter tallies where the averages start with 1, 2 or 3 have shifted to other digits. So even if the averages of voter tallies were uniformly distributed across all 9 digits prior to the experiment, in a large sample, the bias towards the lower digits would remain. This would be the case unless the data is produced artificially, because if the data is produced artificially, then the randomness would be built in the system rather than the randomness over constant averages obtained via experiment. Now, this is not the only force present. Other factors would deviate the actual data from Benford's distribution. The confluence of those factors will present a distorted Benford's distribution. Yet each of these distortions must have an explanation, and by comparing these distributions across different factors, we can take comparative differences through use of controls. This is the way to proceed to compare different data and see whether the Benford's distribution or Benford's law's generality is being followed across the data.